Hello, YouTubers. I have well, somebody asked me if I can put together some work on a centrifugal pump, and at that time, my SolidWork was down. I crashed a few weeks ago, and so I end up doing everything on Fusion 360, the version that you don't need a license for it. Unfortunately, I quickly discovered that that version of Fusion 360 uh, I cannot do. I mean, obviously, this type of simulation. There's a version there, or there's some add-in that you can use, but again, not having the proper license was kind of crazy. But anyway, I did. For example, all the part that you see here were done in Fusion first, and this is Fusion 360, but not. See, I end up trying downloading this Fusion 360, the trial version, because only one thing. Let me show you how they looks like here. Like for example, let me animate this model here. So this is basically the pump that I can come out with. I will show you later the parameters that are important for here. For example, the flow rate. He asked me to design a pump for at least 4 GPM at a 2 meters head here at the output. The input was basically atmospheric pressure. So I end up designing this kind of a centrifugal pump without the volute because of such a small flow rate. Anyway, the story is this. So I did all this on Fusion, the 360, but not this version. That version, at the time to do the export, that was a problem because for the export, it lacked pretty much everything. The only thing that was left, I think, that was the STL. Thank God that you can do still STL on that version. And using through STL, I export the three part that are basically here. I show four here, but it's basically three part. The center here, the shaft is not a big, it's not required for anything else. But so you take a look here. Let's see if I can grab my mouse here to see this part. I did it so you can sort of like you can see through like a crystal type of surface. Anyway, so you can see the inside the impeller, and pretty much the way it should be. So the next part was how I can export this into SolidWorks. But this version is great because this version has all the power to do export in so many you can do so many type of exporting which are shown here, which is great. I mean, one of these should work. Obviously this one was perfect, this one here. That's the one that I use. Export everything, my three parts, and into SolidWorks, and reassemble them in SolidWorks. And I'm going back to SolidWorks here, and actually I have a couple things here to show in SolidWorks, like for example, can I see this? Oops. Oh, here it is. That's the some of my import. That's the basically for the impeller, how it looks like, you know. And when I was getting it, I saw all the other parts are shown. But now going back to the main one is this. There we go. Now, as you can see, I'm doing the simulation using a rotational region, and that was kind of a messy to understand how SolidWorks will do that. You know, I want to. This is just a very short video of that what can be done, not how I did it, because it takes a while to set few things here and there. But one of them is very, very important. You gotta enclose this guy into a box. You had to put a box there big enough to so you don't see it at all. Here's the impeller, and we create what we call it a rotating region, and that's basically is to cover, create an enclosure to cover the full impeller as shown here. So let's see. Oops. And so you bring the impeller into the picture because you don't want to make it big or too small. So you want to be sure that you cover everything. So you bring the impeller into SolidWorks, and basically is this the one that I migrate from Fusion, and the next part is you select this side as your top plane, and then you do in this case the sketch. I'm on the sketch right now, and the next thing will be to extrude that circle, which is about 51. It's a slightly larger than the diameter of the impeller. So the idea is to create that uh, rotating region. So with that said, we are here, and that's basically it. You extrude it, and whatever you have to do. Like for example, here the impeller height is about 16 from bottom to top, so I add 1 millimeter more to 17, and so that's how this works. And the diameter is slightly bit larger as well as 51, as I said. So uh, and and that will create uh, the rotating region. And with that said, basically um, you save that as the rotating region, and then you go into assembling, and you have this part, and you have also the impeller and everything separated, but you already have the proper size for the rotating region, and that's basically it. And that was kind of for me like a what I'm doing that. So but I read about it, and that's what they said. You have to do a box, and that box will enclose the rotational region, because otherwise you cannot pick it up. You cannot pick the impeller as your rotational region. It is not. It has to be this empty space, which is included as part of your box that you put around it. So so when you do the assembling, you do the three parts. I mean, well, let's see. Well, the three parts, because basically is the housing, the impeller, the lead of the pump, and those are the three parts. But now there's a fourth part coming, which is this one. There is the box that will enclose everything, and that you end up having uh, this part here. So the rotational region is basically a box that is covering the impeller. So you can see there pretty much how it looks like. The impeller is right there. It's not really moving, but what is moving is the effect of the liquid doing the rotation and eventually coming out of this way. You can see very red. The red mean very high pressure. Well, relatively high pressure against the input pressure was basically atmospheric somewhere here. As you can see, there's a deep blue down here, meaning if I rotate this a little bit, meaning that somehow I might be around somewhere here. A little bit of a vacuum maybe being created here. And one funny thing is I didn't put, there's a ball bearing here somewhere that I didn't add that ball bearing, and so there's flow up to the some of these what they call it, some of these create leads. You have to kind of enclose the volume that you will be analyzing. So flow go right through here, and this is where the shaft uh, was to be located, and this is the output. The three of them have to be sealed, otherwise you will be in trouble. This the simulation will not work. So I put the three leads on it, and do now the other part is what are the boundary conditions, so this make it start to make sense. The boundary condition, like for example, that I pick is, let's say that the static pressure, that's the where the flow will get into, is about atmospheric pressure. So you are not, you don't have any head up into the pump. So you need to suck that water, because that's basically my fluid, with water in, and the pump will do his trick to raise pressure to the level of the red. The red is about 151,401 Pascal. So I don't know, a meter, what in water meter that might be about 15.4 water meter uh, of that water coming out because it's rotating. That guy is rotating. We check the definition here to about minus 4,000. And the minus is because I want it to rotate counterclockwise. If I put the 4,000 positive, it would rotate then uh, clockwise, which is not the case. I don't want that. So if I'm out of here, I don't have to change anything. Anything else about the outlet? The outlet flow, if I reduce this a little bit, it was for about 4 GPM. 4 GPM translated into cubic meter per second, that number that is shown there. And as you can see, there's not much to say except that it did analysis. And let's see, machine is a little bit slow. So, and I like it because you can see the different colors as the pressure start rise from the eye of the palm up to getting to this yellow color that's getting into the red color. Now, uh, there's some measurement of torque. Obviously, the torque that I'm interested is in the y direction, meaning around the y. So I put the three of them, no big deal. What else? The flow was a leftover from something else I was doing at one point in time. Not, it's not required. I don't. I think that that's basically it. Now the gold plot, maybe I need to revise this, edit definition. The only thing that I'm interested here, I don't need this, is only the torque. So show the torque, and that's the value, about zero point 0.1 Newton meter, zero point 0.1 or whatever, being the maximum about zero point 0.2. So obviously I take this number with with caution, since I haven't done any more mesh improvement. I use the mesh basically without, pretty much the way it was, no improvement at all. So you might be surprised how much this number can change as you get a smaller mesh size. But again, that's based on the type of computer you have. You have a fast computer, perfect. You have a slow computer like I do, then that would be a problem. We'll stay here forever, and we don't want that. But again, it's kind of interesting to figure it out that this value is close to what I calculate by hand. And here is my Excel spreadsheet where most of these calculations were done prior doing any drawing on Fusion, or eventually translating all those files into SolidWorks. All the parameters were checked here against this table based on the pressure rise equation, and you can change the RPM as required. Like for example, I put 4,000 back there, so that's 4,000, and the torque is about 0.05 small torque. Now you check the calculation of the torque in Newton meters based, and all this, I mean, this R1, R2, all those calculations were introduced into the model, and based on that, and let's see where we are now. So 0.05 torque. Now check what my calculation based on this guy were. 0.076, no bad at all. 0.076, 0.076. Let's see. Let's do something quickly here. That's 0.076. Let's put that number here. 0.076. A little bit higher than the torque that I'm showing here. So basically, this is the ideal torque. Is this? Let me do it. Yeah, let's see. Divided by Uh, that would be B23, about 71% efficiency, if we can believe all those numbers. So that would not be bad at all. I mean, I thought it would be worse because I don't have a volute on this design. I only designed the impeller, and that's basically it. And this is tiny pump. So, I mean, most of these numbers are not that easy to get just because you don't have much information when the pump get to less than 10 GPM. You have to work yourself around and try to come out with numbers that make sense, like this radius 1 and radius 2 for the impeller and so forth, and the thickness of the pump. And again, this was for 4 GPM, which end up being about this flow in meter cube per second, and you get all that calculation. And I don't want to bore anybody. It's just that the point is that I'm trying to make here is, can be done. Yeah, it can be done. It takes time. I mean, it's you know, you got to understand many things. Like for example, how I was able to get this work done in Fusion 360, a version, the freebie version, but eventually have to get the the one that is only for a trial. And the idea of that trial is that um, going back here, by changing my account, I go back to my regular Fusion, which is very limited in terms of exporting whatever I need to export. So you will be left with only very few here, if any, which is bad. So again, this is for only, I got only left, this was 30 days, I got 28 days. So I did all this exporting a few days ago. And so now you have it. The What I'm gonna be doing lately is I wanna, you know, go through. Let's see. What I wanna do actually, I have a very bad mouse, so I have to do all this flipping because my mouse is not does not want to work properly. So uh, I want to do and check how much this torque change as I increase the RPM or drop the RPM. It's sort of like a table in where I see how much head you get here as per RPM. At 1,000 RPM, you get a value, and 2,000, 3,000, 4,000. Right now, I'm 4,000, and I'm in the red zone here. So uh, there's other way to do this type of simulation, but that is called slippery surfaces or something like that in SolidWorks. But I guess I will leave it up to here. That's it, no more. This simulation confirmed, yes, that the numbers make sense. You can push water 4 GPM with a decent amount of head here at the output. And the only thing that you need to worry whether cavitation will happen here, I don't know. It's a very low. I mean, 94. It's under vacuum, but depends on the temperature. Uh, you need a steam table or something like that to check whether what pressure water will boils. But 94, I don't think so. That water will boil at this low pressure. It has to be hot. The water has to be hot to start to boil at this low pressure. So in other words, if you are pushing water at 25 degrees C, um, it's, it's not going to boil at this low pressure. That's what I'm saying. Well, folks, that's more than enough for this video. Again, this video is not how to make all this to work. It's just to show you that it can be done with patience. You have to pay a little bit of patience and have the will to do it, because my my SolidWorks crashed, and so I start with Fusion, one part of Fusion, move to another Fusion part, transfer the files into SolidWorks, and eventually assemble the whole thing in SolidWorks, and then complete what I'm doing here, which is basically the simulation, and to finally start to compare the numbers that this is showing versus what I did by hand. That's it. Have a great, great, great day. Bye.